Cool. Aha. So background saving. Yes, I mentioned this earlier. Our favorite animated overlay is this. And you may remember it had featured in my flame graph of bad things going on. And this thing doesn't arrive until 700 milliseconds after the save has started. Just so you know, like we try and not show it to you. So for small documents, you should never see it. But for larger documents, yeah, not good. So, well, profiling before optimizing. Yes, good. So we looked at that, and this is a week-long profile of our usage. Of course, load is something that, again, mentioned plugdex, Ash's talk earlier, that we're looking at, and to some degree, it takes time to load things. It's actually interesting that it takes significantly less time to save things, and things are saved quite a lot. So I don't know, this is, anyway. So our save is obviously far more optimized than our load for whatever reason. Perhaps because we're just copying streams in lots of cases. So instead of uncompressing images or doing clever things, we're just whacking stuff back into a file. Nevertheless, this is quite a big chunk of stuff that is blocking us. So a key concept here is a wonderful Unix feature of fork function and copy on write. And copy on write is a complicated topic to deal with. So I asked ChatGPT-4 to create a diagram that would explain copy on write RAM usage after fork. And this is what it came up with, which I think is creative. When I see Tironte of that, and there's a cow in the middle. So there you go. Well, this is yes, you're right. That's the RAM. Yeah. Okay. Well, anyway, so essentially what happens when you call the fork function, it's one of those very interesting C functions. You call fork and you get two of yourself. It's like, clone the multiverse on your CPU. Suddenly there's two of you. And anyway, all the memory that you had is then, well, it's two processes see it, but very little of it is duplicated. Only as you write to this, will it then be duplicated into this process's address space. Does that make sense? Which do you prefer? Hands up for this one or that one? I don't know. Anyway, so yeah, I was hoping to save time, but it turns out. Anyway, so it's easy then. All we need to do is we, instead of getting this guy to save, we just fork and then we save with this one, right? Easy money, no problem. Yes, well, anyway, except for the following points, it's an exact duplicate of the parent. Obviously, there are some slight differences. Yeah, but it's a kind of a funky function, isn't it? It has a different return value depending which multiverse you're in. So there you go. So one of the problems is that you can't fork with lots of threads, or at least you can fork with lots of threads, but if any of them are holding a lock, it will still be held in the child and never released, which can be bad if that's the main allocator lock, for example. You just don't get to allocate any more memory. So first we need to join all the threads. So there's a new method that says, hey, squash yourself down to one thread. There's a proc self task thing, so we can actually check that the code actually did that, because it's quite dangerous. You don't really want to get this wrong. So, maybe someone did something funky. They're in the middle of a web download in the background of something. Yeah, well, we're not going to do background save them. So that's fine. We duplicate all the file descriptors when you fork. So yeah, and this is quite exciting because if you can imagine both of these trying to answer the same questions, both connected to the JavaScript at the end, both getting the same keystroke, and then processing it and sending different diffs back, you get very interesting psychedelic screen effects. It's great. So you need to close all of your file descriptors that you don't want, and that's kind of good. And after that, everything should be fine, except it turns out they're sharing the same file system. Okay, so it's a jailed file system, only those two things and that document in it. But it would be kind of nice if, as you saved, you didn't delete the other process's files. That's kind of useful. So I was very slickly happy that this was working swimmingly until the second save failed because the first one had deleted the document. Anyway, so yeah, so that was good. And then there's a number of optimizations, like all of this. Let's save memory by going around and touching lots of pages and compacting. Actually just waste memory in this case. So it would be good to turn that off. And yeah, so we should exit it really hard. We can't actually kill it, but we can underscore exit to get out of it. And there are real problems with permissions that we work around with clever tricks in the parent process that we can't do in the child's process because we've lost permission to our own proc filing system. So anyway, like I said, 700 milliseconds there. We get it down to about, well, 6 milliseconds is what the fork takes in the first case. Probably there's some additional cost as you type and mutate and copy pages. But I like to think 100-ish times faster is kind of nice. And I was encouraged by Raymond, you know, saving every second. Hopefully this will, you know, make his life somewhat quicker. And yeah, there you go. And we avoid lots of heap fragmentation on save. So that allocate loads of columns is a one-off nightmare that disappears. So it's not completely finished. We're talking about autosave only for this. There's a magic environment variable to make it happen, and a bit of other things that need doing. And I'm out of time. So ask me afterwards. Thank you.